as we were saying, with all of these problems, starting again from the video here, we have some sort of objective function that we want to maximize or minimize. We have some sort of linear inequality constraints that we need to be true, and we want our variables to be non-negative, so we're talking about the first quadrant. So the graphical approach to solve this whole thing would be to make a graph, to graph your inequalities, and then to shade them. And normally that's going to give you some sort of shaded region like this. We call that the feasible region. And then you look at the corner points. You plug each of those corner points into the objective function, and you're done. That's the whole problem. All you have to do is plug the corner points into the objective function, figure out which one is the max or the min value, and that tells you how to make your business decision. Now that's the graphical approach. Easier said than done? Maybe. I mean, you still have to graph it all and find all those points of intersections, but that's it. So the other approach is to use this idea of the initial simplex tableau. And that means take all this information right here, just the objective function and the constraints. You don't need to bother with the x is greater than 0 and the y and the x is greater than 0. And you want to put that all into one matrix. And so we talked about doing that like this, that you would have your x1, x2. You would also have to introduce a slack variable for every constraint. And since we have 2 constraints, we get 2 slack variables. And then you have to also include your objective function, which is your z. And then finally, you have the number totals at the end. So we're going to take all this information, put it into one big matrix, and we call that the initial simplex tableau. I'll go ahead and do that here for number 27. So my first constraint would be 1, 1, first slack variable, nothing, nothing, 22. And then my second constraint is 2, 1, and then not that slack variable, use that slack variable, no z term, and 12. And then finally, the objective function, remember we move both of those terms to the left so that z is positive. And then we'd have -3, -2, no slack, 1 z variable, and that's equal to 0. So this fella is our initial simplex tableau. Big matrix. So now what was our goal here? What was our goal? I'm going to come over here to write our goals.
Get the bottom positive.
Exactly right. The goal was positive bottom row. Okay, that's our goal, the positive bottom row. Our method, what did we say the method was? Our method was pivoting. That you had to choose some number to pivot around. And once you chose your pivot, that becomes the 1, and you make zeros above and below it. So the method was pivoting, which is essentially creating that Gauss-Jordan look where it's 1, 0, 0, or 0, 1, 0, or 0, 0, 1. The point is that you should have a single number 1 and then zeros above and below it. That's what we mean by pivoting. And then the big question was, how do you choose a pivot? And that was called the simplex algorithm. So the simplex algorithm told us how to choose your pivots so that you can work your way through the matrix and create a positive bottom row. So what was that simplex algorithm? What was step 1? To choose the most negative number from the bottom row. So choose most negative from bottom row. And after all, what is the bottom row representing? The bottom row was the objective function, really. So it's the most negative from the bottom row. Okay. And then once we choose that most negative number, that's telling us the column where our pivot is going to be. That's the column where the pivot is going to be. But we still need to choose which of those numbers to be the pivot. And so what do we do next? We make quotients, which was right divided by left, right? Right over left. We make quotients of the last number with the number in that row. So what we have now here is 22 over 1, and then this would be 12 over 2. And you just make quotients from the constraint column, not from here. Here wouldn't make any sense because you'd have 0 divided by -3. It'll always be 0. So you just do the quotients from the constraints, and that gives us 22 and 6. And which one do you choose? Yeah, you choose the smallest. And that tells you which row to choose. So we wanted our pivot to be in this column. We wanted our pivot to be in this row. So we're choosing the number 2 to be our pivot.
So number 2 has to be 1.
Yeah, we want to turn that into a 1 and make those zeros. That's our goal now. So we go ahead and pivot. That's what we do. We pivot around that number. And then step 4 is just, if you successfully made the bottom row positive, you're done. And you can read the simplex tableau for your answer. If the bottom row is not all positive, you go again. So you're either done or repeat from the beginning. Okay, so let's go ahead and try it. We want to turn this into a 1, and we want to make that a 0 and that a 0. That's the essential role of pivoting. So what would be easiest here? Probably just go ahead and divide this whole row by 2 to turn that into a 1, since we want that a 1. So I'm going to go ahead and do that. I'll turn that row into, so that would be 1, 0.5. I like using decimals. 0.5, 0, 0.5, 0, and 6. And I'm going to rewrite those 2 and rewrite this. So all I did so far is just divide that row by 2 to create that into a 1. This is still my pivot. And now I want to get rid of that 1, and I want to get rid of that -3. So how do I cancel a positive 1? A -1. So I'll multiply this whole row by -1, so that's -1, -0.5, -1, -0.5, times -1, times -1. So now I can go ahead and add the middle row into the top row. So that'd be 0, 0.5, 1, -0.5, 0, 22 minus 6 is 16. Keep my middle row, because that row is already done. And now I need to cancel out my -3 with a +3. So I'm going to multiply the whole middle row times 3. So it gives me times 3, times 3, times 3, times 3, times 3, times 3. And I'm going to add that row into the bottom to create my 0, my -0.5, my 0. Oh no, did you see what just happened? I still have a negative number. So what does that mean we have to do? We do the whole thing over again, right? So I go back to step 1 of the simplex algorithm. Choose the most negative number. Well, that's the most negative number. And now make quotients. So I come over here and I say 16 divided by 0. Well, that's undefined, so that can't be the choice. And 6 divided by 1, that's equal to 6. That's the smallest number. So I'm looking at my pivot. Okay, so what do I want that number to be? Since it's my pivot, I want it to be a 1. So I'm just going to go ahead and multiply that whole row times 2 to turn that into a 1. So now I have 2, 1, 0, 1, 0, 12. And, oh, you know what? Maybe that was silly of me. To cancel out the 0.5 and the -0.5, don't I want to leave it as a 0.5? Yeah, well, I still need to turn this into that anyway, but I can go ahead and cancel those 0.5s right now. For instance, I can just add the second row into the third row, and that would create a 0. So adding that to that, to that, to that, and to that. Oh, and you know what, folks? I can already tell I'm done, because look at my bottom row. It's all positive. I'll go ahead and finish, though. So I multiply the middle row times -1, so -1, -0.5, -1 times -1 times -1 times -1. Add it to the top row. That gives me -1, 0, 1, -1, 0, 10. And now I truly am done, because my bottom row is all positive. So now what? This is the initial simplex tableau. We talked about how to read this. I can read this variable. I can read this variable. I know my value of z. So what do I get out of this? This was my x1, x2, s1, s2, z, and a number. So what can I conclude? What's my value of x2? 12. So I'm going to come up here and say x2 is 12. What's my value of s1? 10. So s1 is 10. And what's my value of z? 24. So what I now know is that z equals 24 is the maximum value of z. And that's what the problem asked me to do. That was the fundamental thing it asked me to do. Well, okay, these instructions are different, but the idea is to maximize this function. And so I just maximized the function provided x2 is 12. And now I can go back and double check. My z function is 3x1 plus 2x2. So if my z max is 24 and my x2 is 12, what does that mean my x1 must be? 0. Because 2 times 12 is 24. That's already 24, so x1 is 0. So our solution is x1 is 0, x2 12, and what coordinate is that? That's the coordinate 0, 12, which was this corner point. So apparently that was the corner point that would have produced the maximum value of the z function. Oh my gosh, is that just not so much fun?
Love it.
Are you all feeling a little more comfortable with it now? We've now had 3 solid class days of working with matrices, let alone inequalities, and so I'm hoping that that all feels better now. Yep, that's the whole problem. Boy, that was fun. That was amazing. Any questions, any thoughts before we move on? These markers are kind of dry. Like my humor. All right, well then. So that's what we finished the other day, was the simplex algorithm. And really, what is a simplex algorithm? What are you really doing with the simplex algorithm? Choosing pivots, right? The simplex algorithm is choosing a pivot. And by choosing those pivot, it allows you to get the bottom row positive and then you're done with the problem. So now, the very last section of chapter 4 is to talk about duality theory. And so everything that we just did here with the simplex algorithm, this was for maximization problems. This was for maximization problems. You can only use the simplex algorithm for maximization problems. That's what it's designed for. So we would like to now be able to solve minimization problems. And so what, did we already do number 29? Yeah. Yeah. So we're going to do number 30. Wait, let me look.
Let me make sure that 30 is the problem we shall do.
No, not 30. We're not going to do 30. We're going to do 31. So everyone go ahead and flip to 31. You can cross out 30. We'll never do it. The only time you'll ever see number 30 again is in your dreams. So here's 31, nice and big. And we're saying, hey, I want to minimize this problem. Now keep in mind, we could still do the graphical approach. And I want you to take a look here. Notice that these inequalities are greater than inequalities. So which way do I shade the inequality? If it's greater than. I'm shading up now. So look at what the graphical solution would produce. The graphical solution would produce something like this, where my corner points would be here, here, and here. And this whole region, the feasible region, is now infinite. So that means to work your way down as far as you can into one of these 3 corners, and you want the value of your coordinate to be as small as possible. So it's either going to be that coordinate, or that coordinate is going to produce the minimum value of that objective function. So it still works the same way. Even though the feasible region is infinite, you're still looking for one of those 3 corner points to produce your answer. And this problem is easy. We could just do it this way. You just graph it. Look at the corner points. But instead, what we like to do is use the simplex algorithm. But that's only for maximization problems. This is minimization. So what was the tool we learned for turning a minimization problem into a maximization problem?
We had to like switch the columns.
Yeah, we switched the rows to columns, and that was called the transpose. The transpose. So first, okay, so step 1, you have to write down the A matrix, just a regular matrix containing that information. And recall, we did that by putting in the constraint z function. So the first constraint was 3, 2, 60, and 4, 1, 40. And then the z function, you simply put in the coefficients from, the w function, that's a w. You just put in the 4 and the 2 and a 0. And that bottom right-hand corner is always 0. So that never changes. And so what we've done is we've just taken the information from the constraints and the W objective function from the minimization problem, put it into a matrix we called A, and now we're going to compute the transpose matrix. So we turn each row into a column. So we say, okay, the row 3, 2, 60 becomes the column 3, 2, 60. And then the row 4, 1, 40 becomes a column 4, 1, 40. And then the row 4, 2, 0 becomes the row 4, 2, 0. Now what we're going to do is very carefully extract the information back out of that matrix. So for instance, this information was y1, y2, and the numbered term with our w function down here. So now this is going to be x1, x2 with the number, and this is our z function. And this is now a maximization problem, whereas this was a minimization problem. So step one was to turn our minimization matrix A into our maximization matrix A transpose. Now, we still need to get all that information out and put it back in a form we recognize. So what do we have here then? Keep in mind, everybody watch very closely as I do this, these inequalities were greater than or equal to. So when we do the transpose, they're going to become less than or equal to. Because we're flipping this around, turning a minimization problem into a maximization problem. So now let's write down what we have. We want to, I'll do the z function first. We want to maximize z equals 60x1 plus 40x2. Because now we're using x variables in the maximization problem. One of our constraints, so subject 2 would be 3x1 plus 4x2 is less than or equal to 4, and 2x1 plus 1x2 is less than or equal to 2. And that's the problem we're interested in. Now what do? We take all that information and we put it into one big matrix. That's called our initial simplex tableau. So my one big matrix is going to have x1, x2. We're going to have a slack variable for each constraint. So I have slack 1, slack 2. We're going to have our z function in there, and we're also going to have a number to represent the totals at the end. So there we're starting to make our initial simplex tableau. So now we can go ahead and put all that information in. We have 3, 4, the first slack variable, no slack, no z, and then the number is 4. And the second constraint would be 2, 1, no slack, we use slack 2, no z, and the number is 2. And then the bottom row is the objective function, which we write down by moving all the terms to the left as negative. So that'd be negative 60, negative 40, no slack, 1z, and the number 0. So we're now in a position to do the simplex algorithm, which again just means make the whole bottom row positive by choosing the correct pivot and doing matrix. I'd like to point out that at this point, the fact that all this works is like pure magic, right? I mean, it basically just feels like we're manipulating a bunch of numbers. Why should this work? Why should this result in the correct answer? These are great questions. The textbook does a little bit to explain why it does work. And we're focusing on using the technique. Everyone ready to do the first one? Or, the first pivot. So what's our step 1? What do we choose?
Negative 60.
Negative 60. Step 2, we have to make our quotients. So we're going to divide. Over here, 4 divided by 3 is 1.3, repeating. And 2 divided by 2 is 1. So definitely the smallest of those is, the 1. So that means we're going to do this row, this column. So here's our pivot. So our pivot is the number 2. We would like to turn that into a 1, and the number above and below it into a 0. So what should we do first? Should we turn this into a 1 and then just cancel out the 60 and the 3?
Yeah.
Yeah, I mean, why not? So we'll go ahead and turn that into a 1. That'd be dividing everything by 2. 1, 0.5, 0, 0.5, 0, and 1. And now we want to cancel out the positive 3. So I'll multiply that row by negative 3. So negative 3 times negative 1.5 times negative 3 times negative 3 times negative 3 times negative 3. And then we'll add that into the top row. So negative 3 plus 3 is 0. And negative 1.5 plus 4 is 2.5. And 0 plus 1 is 1. And negative 1/2 plus 0 is negative 1.5. And 0 plus 0 is 0. And negative 3 plus 4 is 1. So there's that one. And now we want to cancel out the negative 60. So we need a positive 60. So I'll multiply this whole row by positive 60. So times 60 times 60 times 60 times 60 times 60 times 60. And we're going to add that into this bottom row. So 60 and negative 60 is 0. 30 and negative 40, oh darn it, it's negative 10. Does everyone feel that same disappointment? Because we have a negative number, we get to do the simplex algorithm again. Nice. We did successfully pivot. We created a 1 with zeros above and below it. But we get to do simplex again. Anyone, you know the word simplex sounds a lot like the word simple. You know, just take off the letter X and you have simple. Anyone feel like this is simple? Maybe they should call it the hard X algorithm. No? No? Or the long X algorithm? No? Okay, so doing it again. Choose the most negative indicator. Well, there's only one negative number now. That's 10. And again, we form the quotients. So notice 1 divided by 0 is undefined, so that can't be it. And then 1 divided by 1 is 1, so that is it. So we're looking at this row, this column, and so now this is our pivot. So we want to turn that 0.5 into a 1. We just multiply that whole row by 2. So then we'd have 2, 1, 0, 1, 0, 2. You'll notice that row is back to what it started as. And now we can cancel out the 2.5 and the negative 10. So to cancel a positive 2.5, I multiply by negative 2.5. So times negative 2.5. So times negative 2.5 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 times negative 2.5. And then we add that into the top row. So let's see here. Negative 5 plus 0 is negative 5. Negative 2.5 plus 2.5 is 0. 0 plus 1 is 1. Negative 2.5. Ooh, plus negative 1.5 is negative 4. 0 plus 0 is 0. And negative 5 plus 1 is negative 4. Now we want to cancel out the negative 10. So we need a positive 10. So we multiply the whole row by 10. 2 times 10. Okay, times 10 times 10 times 10 times 10 times 10 times 10. And then we add those into the bottom row. So that would give us 20, 0, 0, 40, 1, and 80. So that's very exciting. We have the bottom row is all positive. We're ready to now interpret all of our results. We have a column of 1s and 0s, another column of 1s and 0s, and we have our z equals. Now, the information I just circled would be the information problem. In the maximization problem, what we can now say is that we should label our headers here, x1, x2, s1, s2, z, and a number. So now we know in the maximization problem that x2 is equal to 2, and s1 is equal to negative 4. It seems fishy. And z is equal to 80. Okay. That's for the maximization problem. The maximization problem isn't actually what we wanted to solve. What we really wanted to solve was the minimization problem. But what duality theory tells us, this whole theory of using the transpose matrix, duality theory tells us that the max of the max problem, 80, is equal to the min of the min problem. So the minimum value of W is 80. We're guaranteed that by duality theory. But we still need to solve for y1 and y2. You know, what values of y1 and y2 do we plug in to actually produce that minimum value of W? And this is the other exciting part about duality theory. These slack variables in the max problem, the very bottom row, represent the y1 and y2 from the minimum problem, y1, y2. So you could go ahead and say that this is the z, and it equals 80, and so this is y1 and y2. So now let's check. We're saying that W is the minimum value when y1 is equal to 0 and y2 is equal to 40. Let's check if that really works. If I plug y1 equal to 0 right there, and I plug y2 equal to 40, does W actually equal 80? Yeah. And also, just for kicks here, if you go back and look at my coordinates, y1 is always the x-axis and y2 is always the y-axis. Always the first variable is the x-axis, the second variable is the y-axis. So what we have here is that y1 is 0 and y2 is 40. So it must be this was the coordinate, this was the corner point that we were talking about. So remember, I did start off by graphing what that would look like, and that is relatively what that would look like, and sure enough, it was one of the corner points. Also, folks, look at the objective function that we wanted to minimize. We want the smallest value possible. So just look at those two coefficients. The first one, the variable gets multiplied by 4. And if you want to make your value as small as possible, why would I want to multiply by 4 if I could just multiply by 2? Multiplying by 2 is not as, that increases the value less. So it's almost a foregone conclusion that we would have wanted to put all of our quantity into the times 2 and none of it into the times 4, because the times 4 would make this quantity bigger, but our goal is to make this quantity smaller. So you might say, well, geez, if we want to minimize this function, and you can just look at the coefficients and say that's a smaller coefficient, put all of your quantity in there. Why can't you just solve it that way? Well, because you still don't know what the minimum value is. Sure, we could figure out that all the quantity is going here and none of the quantity is going here, but we would still have to find out what that means. Okay, well, yep, that's fine. That's the simplex algorithm and duality theory. What would anyone like to say, ask, or cry? Don't put it on the final. Oh, it'll definitely be on the final. The way the final exam works is that, okay, so for the exam just takes like 5 questions per chapter, and that's the exam. The final will take 1 question or 1 or 2 questions per chapter. So just imagine like this whole chapter 4 was about using the simplex algorithm and duality theory. Duality theory would be the best problem to put on the final, because you'd have to first take the transpose, turn it into a maximization problem, do the simplex algorithm, and then interpret it back to the minimization problem. So this really is the ideal question for your final exam. Adon, I must have misheard you. You said, put it on the final.
Yes.
That is what Adon said. That's what I thought.
So we'd get like 1 or 2 of those, and that'd be it for chapter 4 on the final.
Or even just 1 of those.
Okay.
Yeah, that'd be it for the final. Cool. Yeah. And then I'd make it worth 4,000 points. All right. Well, folks, should we do anything before we move on? Because now we're going to move on and look at chapter 5, which is all about finance.
Plus,
Yes, Bata.
I don't understand. What did you do after you finished the mathematics?
So I was done. So we're all done, and we notice the bottom row, is it all positive? Yeah, so we know we're done with all of our computation. And now it's just a matter of interpreting the information that's here. This problem then remember you look at the two columns that have zeros and ones. And so this column has a 1, so this is the x2 variable. There's a 1 right there, so we say x2 is equal to 2. And that's what I wrote down right here. And then this column, it's S1, and the 1 is there, so S1 is equal to -4. And then remember this bottom two numbers, this column is always Z, and there's a 1 right there, so Z is equal to 80. So that's the solution to this problem. That if you actually had this problem written down, the maximum value of Z would be 80, and that would mean that x2 would have to be 2. So that's the end of this problem. But then I wanted to go back to actually solve this problem. Is that what you're asking? Yeah. So duality theory states that when you use duality theory to turn your min problem into a max problem by taking the transpose, whatever answer you get here for Z, so 80 is the maximum value of this problem, 80 is also the minimum value of this problem. So I got to go ahead and say that W, the smallest value W can take is 80. I just stole that answer. I just took it. So now I said W is 80. So then I had to figure out what were the actual values of the two variables. And as it turns out, the two slack variables, S1 and S2, if you go all the way to the bottom two numbers represent Y1 and Y2. So then it's just a matter of, again, looking here and saying, okay, well, these two numbers underneath S1 and S2, the slack variables, those are the values of Y1 and Y2 from that problem. So, folks, when you look at this simplex tableau, it packs a lot of information, doesn't it? That's a lot of information all in there in one matrix. But does that answer your question? It does? Okay. Sarai, what's your question? Sarai. The manipulation of the matrix stuff? Well, now that's a really good question here. We could always do one more example because I feel like we have the time for it, just to do a manipulation to kind of talk our way through it. Yeah. Okay, so that's one thought. Diego? David? Adan?
Good.
Luis? Oh, sorry, what would you like to know? You sure? What? Do you have any other questions about this material? Okay. Well, so Sadia and everyone in the room, this would be my piece of my advice for you. Okay, my advice. Let's go back a second and look at. We're done with most of this. Let's look at that original matrix that we wrote down. So the original matrix that we wrote down there was 3, 4, 1, 0, 0, 4. Now, Sadia, go ahead and write this down. And anybody else, this is good practice, a good overall reminder. 2, 1, 0, 1, 0, 2. And then we have, oh yes, -60, -40, 0, 0, 1, 0. Okay, and we did the whole simplex algorithm to say that this would be our pivot. And so I'm going to write down the word pivot. So we're going to do some work. And first of all, let's just state what our goal is. When I say that I want to pivot around the 2, what's the goal? What should this column look like when I'm done pivoting? What should that column look like when I'm done pivoting? Perfect, yeah, it should get down to 0, 1, 0. And so you could say that our first goal is to make that a 1. So how do I turn that 2 into a 1? Yeah, divide by 2. So I'm going to go ahead and divide that whole column by 2. And if I do that, dividing everything by 2, divide by 2, divide by 2, I get 0.5. Divide by 2 is 0, divide by 2 is 0.5, divide by 2 is 0, divide by 2 is 1. So there's that part. Now, what's my second goal? I want this number to be a 0. So that's a positive 3. I need a -3 to add on to it to make it 0. The only way to cancel a 3 is to add a -3 onto it. So that means I want to turn this into a -3. What's that? Oh, no, okay. Yeah, so in order to turn that 3, and in fact, Sadia, maybe what would help is just to rewrite it again. I'm just going to write the numbers again. 3, 4, 1, 0, 0, 4, and then negative 60, negative 40, 0, 0, 1, 0. Okay, I want to, I wish this were a negative 3, so that if I added negative 3 plus 3, I'd get 0. So I need to turn this into a negative 3. How do I turn that into a negative 3? A negative 3 times that whole row, that would give me negative 3. Negative 3 times a half is negative 1.5. Negative 3 times 0 is 0. Negative 3 times a half is negative 1.5. Negative 3 times 0 is 0. Negative 3 times 1 is negative 3. So what I just wrote down there in blue is just what that row would be if I did multiply it by negative 3. And now I just get to add the middle row onto the top row, and that will transform the top row, but I get to keep my middle row the way it was. So I'm keeping the middle row right as it is. I'm going to go ahead and write it down again. I'm keeping my middle row. And what I'm going to do now is add my transformed blue row onto the top row to create a new top row. So negative 3 plus 3 is 0. Negative 1.5 plus 4 is 2.5. 0 plus 1 is 1. Negative 1.5 plus 0 is negative 1.5. 0 plus 0 is 0. And negative 3 plus 4 is 1. And that did it. That turned that one into a 0. So you'll notice that this middle row, even though I multiplied it all by negative 3, I just multiplied it by 3 just to know what it would be. But I still kept the middle row the same. Whereas the top row, I did change it. Now I'm going to change the bottom row. I want that number to be a 0. So what would I have to add to negative 60 to get a 0? 60. So I'm going to multiply this whole row by 60 now. So I'm going to multiply this whole row times 60. So that'd be 1 times 60 is 60. Half times 60 is 30. 0 times 60 is 0. Half times 60 is 30. 0 times 60 is 0. 1 times 60 is 60. Now I'm going to add those numbers together to make my new bottom row. So 60 negative 60 is 0. 30 and negative 40 is negative 10. Oops. Negative 10. And, oh yeah, 0 plus 0 is 0. 30 and 0 is 30. 0 plus 1 is 1. And 60 and 0 is 60. There we go. That's an example of the row manipulations. And really, that's all we ever do. We divide a whole row by a number, or we multiply a whole row by a number, and then you add a row into another row to turn it into a 0. So I'm going to leave this here for a little bit, and then we can talk more after class. And anybody else, if you have questions about all these matrix manipulations, then talk with me, either during break or after class.
I have a question.
Yes, sir.
When we divided for the second time over there, I thought we divided on the column that we did.
What about it?
So for the second division, I thought we divided 1 divided by 2.5, not 1 divided by 0.
Oh my gosh, did I do that incorrectly? Well, that makes a lot of sense. You're right. It's supposed to be, you're dividing by the numbers in, you're right, that's my column. There you go, yes. That's my column, so I should have done 1 divided by 2.5 and then 1 divided by 0.5. Now, had I done that, that would have changed a lot. Wouldn't it have? Let's look at that. Had I done that, boy, Diego. So I'm doing 1 divided by 2.5, which is a teeny tiny number. I think that's 0.4. Is it 2 or 5? Yeah, 0.4. Whereas 1 divided by 0.5, oh goodness, 1 divided by 0.5, oh no, that's 2. So that actually would have changed our choice of a pivot, wouldn't it? That means that we would have pivoted the top, because that's smaller, so we would have pivoted that number. And yet, the solution we came up with is the correct solution from the back. Did anybody, hold on, where's my answer key? Does anyone see the answer on the back?
It's not the same.
It's not the same? Oh my gosh. You're saying we did that whole last problem wrong. I did that whole last problem wrong. So apparently, yep, I chose the wrong pivot. Well then. Everybody, let's take another look at that problem. I can't believe it. I am mortified. So, what does that mean then? We should have pivoted Let me erase all that. Let me erase all that. We should have pivoted. Let me go back to my number here. 2, 1, 0, 1, 0, 2. We should have pivoted this number, which is unfortunate because 2.5, we're going to have to do some quite the extreme division. So we're going to divide that whole row by 2.5. So it'd be 0, 1, 1 over 2.5 is 0.4. Negative 1.5 divided by 2.5 is negative 0.6. Yep, and then 0 divided by that is 0, and 1 divided by that is 0.4 again. Okay, so that's the actual row we have, and we want to pivot that and make the other one 0. So if I want to get rid of the 1, we'd multiply through this row by negative 1, so that'd be 0. I'm going to do it on top. 0, negative 1, negative 0.4, negative times negative 1, times negative 1, times negative 1. Bottom, or the middle row, then that'd be 2. That'd be 0. That'd be negative 0.4. That'd be 1.6. That'd be 0. And that would be 1.6. All right, that's where we're at so far. And then we have to cancel out a negative 10, so we'd have to multiply by a positive 10. So times 10, times 10, times 10, times 10, times 10, times 10. We're going to add that into the bottom row, which would be 0 plus 0, 10 plus negative 10, 4 plus 0, negative 6 plus 30 is 24, and 0 plus 1 is 1. Ooh. And 4 plus 60 is 64. Was that the value, 64?
Yeah.
Oh boy. Okay, so now what does that tell us, folks? Well, we have, let's see, x1, x2, s1, s2, and z, and the number. And this number right here, in terms of reading this answer, we could go ahead and make that a 1, because this is going to be our column of zeros and ones, and that's a column of zeros and ones. So what we know now is that 2x is equal to 1.6. So 2x1 is equal to 1.6. That means, dividing off the 2, that x1 is equal to 0.8, and x2 is equal to 0.4, and our z value is 64. So what we know now about this maximization problem is that those values will produce a max value of 64, which means the minimum value that we can get over here is 64. And then, as I said before, the slack variables, S1 and S2, these numbers down here represent the real values of y. So this is y1, y2. Aha, which means that over here now, y1 is 4, and y2 is 24. That's really interesting. I wish that I hadn't deleted my picture yet, because that means that, in fact, it was not that corner point up there that was the minimum. This was the corner point right there. So the corner point was 424, that one in the middle. And that produced the minimum value of 64. Okay, well, boy, that was a costly mistake. So yeah, Diego, thank you so much. My brain, I divided by the first numbers instead of the numbers in the column that I chose from the simplex algorithm. But all the manipulations are still the same, and the results you still read off the y1 and y2 value from the s1 and s2 column. Boy, and what time do we normally take a break? 3? Maybe now would be a good time to take a break. Let our brains take a break, and then, plus we're going to start an entirely different chapter. So let's go ahead and say right now it's 2:50. Let's everybody come back at 3. And that'll give us a good chunk of time to start chapter 5. And Diego, thanks for pointing that out. Let's take a break. Well, it's interesting to note that by choosing the wrong pivot, it still gave me a corner point. Isn't that interesting? I mean, it's not that it just gave nonsense. It did give a corner point. It just wasn't the right corner point. And that's kind of what the simplex algorithm is about, is choosing the right pivot. By choosing the wrong pivot, it still gave me a corner point, it just wasn't the correct corner point. That's interesting to note.
sir. Okay, and what's your question? What to do? So that's our most negative number. Is that a negative one? Yeah, okay, so you already did the questions? Let's do it again. Okay, so you want to pivot that one?
Yeah, I was sorry.
What is that? Yeah, that's a negative one. Okay, so first of all, we just need to turn that into a 1, and that's a 2. So you just divide everything by 2. So then, if you just divide it all by 2, that'd be 1, 0, 6, 4.5, 0, 0, 0, 30. So that's what that row is. Okay, then what? Wait, this is the problem.
Yeah, this is
Where is it?
this
From the where? From the packet? Oh, from online. And so they gave you this and they just said pivot that number?
No, I don't say that. I just tell you.
Can you show me? Is it on the computer? Okay. Oh, there it is.
It's not yet.
Huh? Oh, okay. Well, when you get it, let me know.
This way.
Did you find it? Okay. Oh, yeah, so in this case, you don't have to pivot or anything. You just want to know what can you read already from the table. And so, like, for instance, in this one, oh, you know what? We didn't cover a sample like this, but see, this one has all just one entry and all zeros, and that's all zeros and just one entry. And so you would say 3x2 is equal to 12. And then you have to solve. So you really divide the 3 off. So you write down 3x2 equals 12, then x2 is really equal to 4. Same thing here, that's 13x3 is equal to 26. So when you divide off the 13, the x3 is actually 2. And this one, find the solutions if you can. That one you can't even. Oh, well, actually, okay. Try typing in 13 thirds. Yeah, try that, see if that's what they want. Divide by 3. Good try. I would need more time to look at this one. That does seem a little fishy. I don't know why. Okay. Yeah, well. 3 o'clock. Okay, let's keep going. So folks, we're about to start a totally different chapter. This might make you happy to know that we're just in totally different material. We're just going to talk about money. So, the way the chapter 5 works is you build up slowly, looking at financial questions from simple to complex. And here we are. We'll get to that. Finance. Okay, I thought you all might want to just write down at a glance all the different concepts we're going to look at. So if you want to take out a simple line sheet of paper and just write down some formulas, there are going to be quite a few formulas that we learn. And so it'd be a good idea to go ahead and have a list right now. Leave like 3 spaces between each term. So start a list, leave, 2 spaces between each term. And let's start writing down some formulas that we're going to do. So the first one is called simple interest. And so that formula is I equals PRT. What does I stand for? What does I stand for? Interest. That's the actual free money that you get. And that's the free money that you get from the bank. That's not the principal that you invested with the interest. It's just the free money. So I's interest, what is the P? And that's your principal. That's how much you did invest. That's your principal. What's R? Now rate. And the important thing is, rate is always communicated as a percent. Like they'll say your interest rate is 3%. But it's always computed as a decimal. So this is one of the cruel realities of finance math, is that people always talk in percentages, but then you actually do your computations in decimals. So how do you turn a percent into a decimal? Yeah, you move it 2 places. So like 3.75%, you have to move the decimal twice, and the actual answer is 0.0375. So that's something important to make a note of, just to remind ourselves that all the interest rates are communicated as percents, but calculated as decimals. And then T stands for time, which is always in years. So even if they say something like months, you have to turn that into a year. So how much of a year is 3 months? If somebody told you you're going to do this investment for 3 months, you actually need to have it in years. So how would you do that? Yeah, you just divide it by 12. So if they tell you 3 months, you divide it by 12, and then that's actually 0.25 of a year. Okay? So, again, it begs the issue of why we even use percentages if we do everything in decimals, and why people talk about anything other than a year, because you have to turn it back into years. Okay, so that's simple interest. Then I'm going to go ahead and cover a couple formulas right now. Then you have compound interest. So compound, oh, by the way, simple interest means you get interest once at the end of the year. So you get
interest once at the end of the year. And that's why they call it simple. Now that doesn't mean that it happens on December 31st. If you start your investment in June, then you get your interest the next June. It's just 1 year later. Compound interest, compound, the word compound as opposed to simple, what do you think the word compound means? Yeah, it just means multiple. So instead of getting interest one time a year, you get interest multiple times a year. So compounded interest just means that you get interest many times per year. And officially, how many times per year? You get interest, instead of saying many, you get interest n times per year. So we use the letter n to represent the number of times per year that you get interest. So for instance, if n equals 1, that's just yearly. That's simple interest. But if n equals 2, we say semi-annually. And if n equals 3, it doesn't, because we don't have a word for 3 times a year. Do we? Do we have a word for 3 times a year? Not so much. We have a word for 4 times a year, and that's quarterly. So if the interest is quarterly, that's 4 times a year, so n equals 4. Do we have a word for 5 times a year? N equals 5? No. Do we have a word for 6 times a year? That's bi-monthly. Yeah, bi-monthly. Okay, and then we don't have 7 times a year, 8 times a year, whatnot, but we do have 12 times a year, and that's just monthly. Is there any larger values of n that we can do? 24. Yeah, then that'd be like semi-monthly, like twice a month or something like that. That could happen, I won't write it down, but you're right, that could happen. And then you could also have n equals 365, which would be daily. A very well-known financial organization does interest daily. Do you know an example of a financial organization that actually computes interest daily? Your credit card company. That's right. When you use your credit card and you don't pay it off at the end of the month, they start charging you interest every single day. That's pretty cruel, isn't it? Whereas when you get interest from a bank, like if you invest money in a bank, you normally get interest yearly or quarterly, right? So, okay, so that's our different values of n. The formula is A, which is the amount of money you have at the end, equals P, your principal, times 1 plus R, which is interest rate, over n, the number of compoundings, raise the power of n, the number of compoundings, times t. So that's compound interest. A little more sophisticated than simple interest. You're just calculating interest once at the end of the year. Yep. Now, there's more formulas that we're going to get to as we work through the material. So just keep your sheet of paper out, and we will write down formulas as we get there. How's that sound? So that way you're going to have a formula sheet. Okay. Well, here we go, folks. Let's begin. Like I said, the very beginning is simple questions. Very simple interest scenarios. You'll notice right up front they have a really weird assumption up there. What are they asking us to assume?
Simple interest for 360 days.
Yeah, 360-day year. How many years have 360 days in them? None. No year has 360 days. How many days are in a year?
365.
365, right? So that's kind of weird. I guess what they're saying is that we're assuming 360 days a year just to make the computations come out cleaner, and that will allow us to match our answers with the answer in the back. Okay, so simple interest. You go ahead and jot down I equals PRT. And so our principal was 3108, and the interest rate is 0.03, and the time should be in years is 8/12. And so you would just use your calculator and compute that. You can type it all in with parentheses. So 3108 times 0.03 times 8/12. Make sure that when you type that in with your calculator, it would actually look like this, parenthesis 8 divided by 12. That's what that would look like. And you end up with 6216. Now keep in mind, how much total money now is sitting in the bank?
3.
Like you put in 3108, but now you have
3,000.
yeah. Now you have 3170. So it really depends on what the question is asking. Do they just want to know how much interest you earned? And yes, that is what they're asking in this case. So that's the interest that you earned, whereas that was the total money that you now have. Okay, so how would we just write down the next one? Who'd like to say? We've got I equals PRT. How do we just write down what we're going to compute? About me, Cheryl. What's my principal? And the rate? And the time?
120, 360.
Yeah, exactly right. And so right there, that's where they want us to use the number 360 instead of 365. Probably because then 120 over 360 is a third, and a third goes evenly into 0.03. Then we get a nice little answer at the end. Right? So what do we get? $10. What? Did I do that wrong?
Did I do mine wrong?
Did I do mine wrong?
Yeah, I got 100. 10,000.
Oh, that's 10,000. There we go. Thank you. All right, so yeah, $100, which means the total is 10,100. Okay, so that's simple interest. Might also ask you to compute backwards to solve for an interest rate. We won't do all of these together. I'll just do as many as we need to see the pattern here. So now they're saying if $3,200 earned simple interest of $132 in 7 months, then what was the simple interest rate? So in all the problems that we do, even something easy like this, you want to start by writing out the formula, kind of writing it really wide like that so you have room to plug in all the numbers underneath them. And they're saying the interest was 132.53. And they're saying the principal was 3,200. And they're saying the rate we don't know. And they're saying the time was 7 months. So how do I write 7 months?
7 over 12.
Yeah, 7 over 12. And so now we want to solve for R. In this case, I'm just going to write 7/12 the normal way. Not to get your hopes up, folks. That's not the end of class. That's just break time.
We get another break?
No. All right, so now how do we solve for R? We've got two things to get rid of. How do I get rid of the 3,200? And divide out the 3,200. And that gives us R times 7/12. And whatever that is, 132. Divide 3. Divide by 3,200. Which is some terrible thing. 0.04141565. Okay, now a note about calculators. Let's say that even though all I wrote down was 0.0414, at this point, everyone should have that in your calculator, right? Like your calculator will have all those decimals of accuracy. And you want to keep all those decimals of accuracy all the way through to the end of the problem. So even if you just write down 4 decimals, you're doing the work on your calculator and you're keeping track of it all the way along. So now that that value is still in your calculator, and we want to solve for R, so what do? You can either say divide by 7/12 or what do you multiply by?
12/7.
Yeah, 12/7. So we multiply both sides by 12/7. So that number that's still in your calculator, you now hit times, and then parenthesis 12/7. And again, that gives you all the decimals of accuracy that you ever hoped for. And now we have 0.070998, etc. Now, right now, would we be able to hit our math frac button and get a fraction? Math frac? Answer, no. But more importantly, do we even want a fraction?
No,
No, why not?
because we want the interest.
You know, this is an interest rate, which even though it's computed in decimals, how do we report our answer? As a percent. So you move it back, and the answer is 7 point. It's said to round all answers to one decimal place. So this would be 7.09, but that means it's 7.1. Notice you're only allowed to round at the end. Like when you're totally done, then you round. Okay, super. So number 4 is for you to do. Have you gone? Okay. So now the next few problems are all about doing compound interest. Now, I understand that probably all of you have already done problems like these. We will get to problems that are significantly more complex. So find the compound amount for the deposit. Now let's really talk about this one. So first of all, they're saying they're giving $7,000 5% compounded annually for 17 years. So first, let's write down the formula together. A equals P 1 plus R over N to the NT. And a best practice that we'll use is to go ahead and run down the values that are in that formula. I mean, you can just write them in order. A, P, R, N, T. So what are we saying about this problem? It says find the compounded amount. That means find the amount at the end. So that's what we're going to solve for. The principal was the 7,000. The rate was 0.05. What's N? 1. Yeah, just 1. It's just annually. And then T is 17. Now keep in mind, since this is just annually, this is just about to compute simple interest again. So if I were to just really quickly do simple interest, PRT, then that's 7,000 times 0.05 times 1 year. Then I already know that my answer should be 7,000 times 0.05, which is $350. But now let's do our formula now. We're saying A equals 7,000 times 1 plus 0.05 over 1 to the 1 times 1. Nope, 1 times 17. Oh. Okay, no, hold on a second. I'm gonna hold off on what I was saying over here. This isn't just simple interest because we're doing it for 17 years in a row. So hold on a second. Let's compare later what happened. Plug in all of your information. The first thing you want to do is simplify inside the parentheses and simplify outside the parentheses. So before you do anything in your calculator, just find out what the inside is. That's 1.05. And just find out what the exponent is. Because those two numbers represent something important. So the inside number, if you draw a little arrow at it, that is how much interest they're actually computing every time they give you interest. So every single time this bank is giving you interest, that's the actual interest being computed. So that's the actual interest being computed. Which, of course, in this problem is obvious. They told us it's 5%, and that's 5%. So you ignore the 1, and you just look at the 0.05. And then the number 17, that's the total number of times the bank is going to hand you money. Okay, so it's important not just to plug that whole darn thing into your calculator and get a single answer all of a sudden. Do just the inside and then do the exponent so you can look at it and say, 17 times the bank is going to give me 5% interest. Then go ahead and in your calculator, plug it all in. And you can just go in order. You do 7,000 times 1.05 to the 17. 7,000 times 1.05 to the 17. And you get the answer of 16,044.13. Round to the nearest cent. Now we're rounding to 2 decimals. Okay, now something happens here though. We are getting, you are just getting interest once a year, but the interest that you get is being put into the bank with the money you already invested, and then you're getting interest on that. So you're not only earning interest on your principal, you're also getting interest on the money that you got in interest from last year. And then at the end of 2 years, you have interest that you throw back into the account, and you get interest on top of the principal and the interest you already earned. So in the end, you end up with this value of $16,044. That's on top of the $7,000 you already had. So if you subtract out the $7,000, everybody, let's go and do that. How much did you actually earn in interest? Right? Because you already had $7,000, and now you have $16,000. How much of that did you actually earn in interest? So you subtract. So that number should still be in your calculator, and you have minus 7,000. And so we actually got 9,044 in interest.
Yeah, 13 cents.
Oh yeah, 13 cents. Whereas, okay, and this is what makes compounded interest compounded. It's that the interest you earn gets put into it, and you start earning interest on the interest. Whereas the simple interest scenario, if I was just earning $350 a year, simple interest, and now if I do $350 per year times 17 years, I'm not going to end up with nearly as much money. That's only $5,950 of simple interest. Whereas you'll notice and that's just them handing me $350 every year, and I take the $350 home and I spend it on ice cream. Whereas if I was putting that interest and dumping it back into the bank account with the $7,000, and I'm building interest on top of the interest I already earned, you can see how significant compound interest is. How much more money did I get from compound interest than simple interest?
Like 10,000 more, give or take.
About 3,000 more.
Oh.
So that's like 6,000 up to 9,000. So that's 3,000 more dollars. And the difference is, the key about compounded interest is that you put the interest in with your principal. So you just keep on dumping that interest in with the principal so that you're growing the amount of money that you're getting interest on. Whereas when we use the word simple interest, that means that they're actually giving you a payment of that interest every year, and they're sending it home with you, and that's not becoming part of your investment. So compound interest assumes that the interest you earn becomes part of your investment, whereas simple interest assumes that they're just paying you out, and you take the money and you go away. All right, so now how would we write down this one? This one is semi-annually. So again, write down all of your data, A, P, R, N, T. So we want to find the amount. The principal is 16,000. The interest rate is 0.08. The N is what? Semi-annually means twice a year. And then the time is 8 years. Okay, this is our first really interesting example here. If you write down the formula first, A equals P, 1 plus R over N, then T. And our principal is 16,000. All over 2, all to the power of 2 times 8. And like I said, it's really important not just to plug all that into your calculator, but to actually find out what's in the parentheses first, which is 1.04, because 0.08 divided by 2 is 0.04, all to the 16th. So I'd like you all to appreciate what those two numbers mean. The 0.04 means that the actual interest that they're computing for you every time they give you interest is only 4%. So twice a year, semi-annually means twice a year. Twice a year, they're actually only going to give you 4% on the money that's invested. But they do it twice. You know, 4% plus 4% adds up to 8%. So they do it twice. And then the total number of times that they compute interest and hand you interest is actually 16. You get money. What's that, Luis? Did I do something wrong?
I was just asking a question. For 2 times 8, isn't it 16?
Yeah, 16.
0.08.
No, you're dividing.
Well, this one is the interest rate divided by 2, so 0.08 divided by 2 is 0.04. Whereas this one is 2 times 8, which is the 16.
That's so it's twice.
Did that answer your question? Okay. Okay, so folks, again, notice in this problem, you're investing it for 8 years, but you actually get handed money 16 times. So the 16 times they hand you money. And each time they hand you money, are you getting 8% of what you have in there? No.
You're getting 4.
They're actually only handing you 4% of what you have in the bank, but they're handing it to you 16 times.
But they hand it to you twice a year, so it makes the 8%, right?
Right.
Okay.
And actually, in the end, it actually makes more than 8%. You come out ahead. That's the value of compounded interest. The fact that you're growing interest on top of the interest that you reinvest, you end up with more than 8%. And that's called the effective rate. You can calculate what your effective rate is, and it's always going to end up being more than the actual rate.
So if you do invest, you want to compound.
Absolutely. If you invest, you always want compounded interest. And if somebody loans you money, you can bet they're doing compound interest because they want to get more from you.
Okay.
Okay, so let's look at number 7 then. And number 7, again, write down the formula. We always write down the formula first, 1 plus r over n to the nt. And in this case, running down our information, A, P, R, N, T, then we want to know the amount. The principal is 400. The rate is 5%. The compounded quarterly, so n equals 4. And then T is 6.
So to like student loans and like car dealerships, you do compound interest. That's why you end up paying more than what usually.
Well, no matter what, you'll end up paying more than what the thing costs just because you're paying interest.
Okay.
But compound interest is worse than simple interest, depending on how you look at it.
Yeah.
If you're investing money, compound interest is better than simple interest because you're going to make more money. But if you were loans money, compound interest is worse than simple interest because you're going to end up paying more money. Yeah. Okay, so now let's plug everything in. So A equals 400, 1 plus the interest rate over the n, all to the nt. And so let's look at those numbers. That's really 1.0125 to the 24. Yeah. So now what does that mean? It means each time they're actually calculating interest on your money, if you move the decimal back twice, you're only actually getting 1.25%. That's how much they're actually paying you. But they do it 4 times a year, and so that adds up to the 5% that they promised you. And then 24 is the total number of times that they're paying you. So that's the total number of times money hits your bank, or money is handed to you. Okay, so then you type all that in and you can get your answer. What do they want to know anyway? The compound? Find the compound amount. So what, they just want the total? I'm assuming they just want the total. Let's go ahead and do this one. 400 times 1.0125 to the power of 24. The total turned out to be 538.94. Now that's the total. How much interest did you earn? David, what would I have to do to find out how much interest I earned? Because some of that's my money.
You subtract by what you put.
Yeah, you just subtract out the 400, and so I only really earned $138.94. That's how much money I got in interest. And that's what the next couple problems ask for. Is they just want to know how much interest did you get. They're not interested in the total. They would just like to know the interest that you got. So you'll calculate the total, and then you'll subtract out what your principal was, and then you'll get your answer. So I'll do one of these with you. Everybody, just to make life easier, you can all cross out number 8. We don't need to do all of these. I gave a lot of examples. So yeah, I'll do number 9, and then everyone can do number 10. So we have, again, writing down the formula first, A equals P, 1 plus R over N to the NT. And you want to run down what is our information? A, P, R, N, T. The amount is what we want to find. The principal is what we know. The rate is 0.07. The N is compounded quarterly, still 4. And the number of years is 3. So 7,000, 1 plus 0.07 over 4 to the 4 times 3. And again, whatever number ends up in that parenthesis and in the exponent, we want to look at that. So that's 1.0175 to the 12th. So what that means is that for this institution, the actual amount of interest that they're calculating is just 1.75% interest on your money, but they're doing it 4 times a year for 12 times that you'll get interest into your bank account. Okay, so we compute that, 7,000 times 1.0175 power of 12, and that gives us 8620.08. I rounded to 1 decimal place. And then you subtract out the $7,000 that you invested, and that gives you to 1620.08. That's the interest earned. And by the way, doesn't that sound attractive? Would anyone like to have $1,600 of free money? Yes, Mrs. Julie, I sure do. How much is that per year? That's for 3 years, right? So that's, oops, wait, sorry, times 3 minus 7,000 over 3. That's $540 per year. Would anyone turn down $540 per year? And then how much is that per month? Well, monthly that's a whopping $45.
Nice.
But hey, who doesn't want $45 monthly? That could easily pay for your Netflix and Hulu account, or maybe just your internet account.
Unless you're a student, then you get those cheaper.
Well, yeah, that's true. Okay, so everyone go ahead and do number 10. I'm just going to walk around and see your work. Go do number 10. Yeah, like for instance, don't you get Amazon Prime for free as a student?
Yeah, and I think it's like Spotify and Hulu you get for like $5 a month.
Really? $5 a month less, or just $5?
No.
50% off.
Just $5.
Oh, nice. Yeah, that looks really good.
Yeah, that
Nice.
that looks really good.
It's like it's like $2 a month or whatever.
How's your orbits go, David? Is that orbits? Good. Nice, there you go. Oops. Really good, Miss Shirley. Nice. All right, well, those were certainly some nice warm-up problems. And to be fair, I mean, that's pretty often what you want to know. If I invest my money at this bank, how much money will I make? That's one question you could ask, very basic question. If I invest, how much will I make? But there are a lot of other questions you could ask that have to do with goal setting. So everyone ready to check out this next one? So the next couple of problems say find the interest rate for each deposit and compound amount. So what I want you to imagine is that you're setting a goal. What if you have a goal of earning a certain amount of money? And let's just say, for whatever reason, you have $8,000 sitting at home under your bed. Is that where people hide money? Under the mattress? That's what people always talk about, hiding money under the mattress.
Or in the walls.
Or in the walls. Yeah, I wonder where the best place is to hide money anyway. In the Yeah, there you go. So I got $8,000, but 9 years from now, apparently, I know that I need to have $13,000 to pay for something, whether it be a car or something else. And so I say to myself, well, you could be thinking about your teenager, right? Like, what if right now you have a 7-year-old, and your 7-year-old, bless your little 7-year-old, they're such a wonderful little child, and you're like, in 9 years you're going to want to drive a car. And in 9 years, that's how much the car is going to cost. But right now, I only have $8,000. And the question is, between now and then, do I really have to go out and work and save more money? Or could I just take the $8,000 I have and just put it in a bank? And then 9 years from now, it will have earned interest, and that will be the money I can use to buy your car. Nice. Okay, I don't know if you believe my whole scenario here. The point is, you have some money now, you have a goal, and you want to know, what interest rate do I need? So and that's what we're going to do, is what interest rate do I need? So everyone go ahead and write down again our compounded interest formula.
Is that what you're doing for your kids?
Help them buy a car?
Yeah.
I don't know what we'll do. I know that we expect them to get scholarships and whatnot for school. I think we might do a match program. Like whatever you save up, we'll match it.
Oh, that's
Like,
that's good.
If you want to get a car, if you can earn 5,000, we'll match it.
Yeah, that's a good idea.
But contingent upon good grades. In bad grades, they get nothing.
They can
So-
walk.
Yeah, exactly. They can walk. You have time to play video games instead of study, you can have time to walk. Okay, so we want to solve for R. So everybody highlight R. We want to solve for R. That's what we're ultimately interested in solving for. And so we get to do some really fun algebra, right? We want to solve for R. So we plug in all the information that we have. We want to accumulate to $13,373.26. We have the principal of 8,000. And then we have 1 plus R over, right now we're compounding quarterly, so that's 4, all to the 4 times 9. So this is just like any standard algebraic situation. You plug in information for all of the variables except for one, and then you can solve for that one variable. So what's our process? What do we do first? R is being divided by 4, adding by 1, raised to the power of 36, and then multiplied by 8,000. So what do we do first?
Subtract the 8,000.
We can't subtract 8,000. 8,000 is being multiplied.
Would we factor it?
We would divide by 8,000. So that little list I just rattled off for you folks is the proper way to do algebra. You look at the variable and you ask what's happening to it, and you use PEMDAS to say what's happening to it. You say R is being divided by 4, adding by 1, raised to the power of 36, and multiplied by 8,000. And you listen to the last thing you said, multiplied by 8,000, and you do the opposite of that. So since the last thing I said was multiplied by 8,000, we divide by 8,000. So now we have this. Now, how many decimals should we keep?
Just a couple.
All of them. How do you keep all of them? Regardless of what you write down right now, your calculator should already have the current answer. So you need to be doing this on your calculator as you go. So I did that number divided by 8,000. I have some long decimal. And even if I wanted to, I could just jot down a couple decimals. But I'm keeping it on my calculator. All the decimals of accuracy. So now I have 1 plus R over 4 to the 36th. So now what do we do? Again, algebra. R is being divided by 4, adding by 1, and raised to the 36th power.
Would we square root 36? Or square it, right?
You would 36th root it. So keep in mind that if you have like x squared equals 9, you would square root it. But if you had x cubed equals 125, you would cube root it. And if you had x to the 10th, you would 10th root it. And right now we have something to the 36th, so you would 36th root it, both sides. Now you might be saying, how do you raise something, how do you take a 36th root?
Yeah, how do you?
Yeah, and so,
Is it
just like
6?
a moment ago when we had R times 7/12 equals something, how did we multiply or get rid of the 7/12? You multiplied by the reciprocal, and that effectively got rid of that fraction through multiplication. What we have here, though, is an exponent, 36. What we can do now is raise both sides to the exponent of 1/36. Because now what do you do when you raise an exponent to an exponent?
Cross them out.
Well, you multiply exponents. When you raise an exponent to an exponent, you multiply, and 36 times 1/6 is 1. And so over here, we're just left with 1 plus R over 4 to the power of 1, which is just 1 plus R over 4. Over here, you can now easily type that into your calculator. Remember, you still have that value in your calculator. How do you do it? In your calculator, it would be the 1.6716575 number, and then everybody hit exponent. And then what you're going to do is parenthesis 1 divided by 36. All right? So exponent, and then parenthesis 1 divided by 36. You need the parentheses on the 1/36. So what do you get?
1.014374998.
Yeah, and even though I'm just writing down 1.01437, I still have all the decimals of accuracy on my calculator. So now what? I guess I didn't need those parentheses anymore. We have r divided by 4 plus 1, subtract. So we're going to subtract 1 from both sides. And again, even if I just write down 0.014 equals r over 4, I still have all the decimals of accuracy on my calculator because I'm doing it all on my calculator. So everybody should actually have 0.01437499976. Now, r is being divided by 4, so you multiply by 4. And this cancels that last 4. R is equal to, now times 4 on your calculator, all the decimals of accuracy, 0.05749999904.
And we would keep it in decimal form, right?
Well,
Or would we put it in percent?
we communicate rates in percents. So we calculate rates in decimals. So now we move the decimal twice, whoop, bloop, and so that gives us 5 point, and we want, I think, 2 decimals of accuracy always. So this would be 5.74. Now you can just assume that that 999 would have kept going had they been able to give us more decimals of accuracy of the dollar amount. So had they actually told us $13,373 and 0.26, 5, this would have kept going as a 0.05749999999. So really, what's our rate? 5.75 is our interest rate. So this is why keeping all those decimals of accuracy on your calculator is really important. You don't want to round at every step. You want to keep all the decimals on your calculator at all times.
How come we wouldn't make it 5.8?
Well, that would be if you rounded it to 1 decimal place.
But it's asking for 2.
Well, I think we should always do 2.
Okay.
And also, I feel that way because from this answer, I feel like I can infer what they intended. What they intended was 7.5.
Okay.
All those 9s would round up to that 4 to a 5, and what they really want is 5.75%.
Okay. Now, if I were to do 5.8 on a test, would I get that wrong? Or
Well, just where do you stop? What if you're like, hey, I want to call that 5% or 5.8, and the next person's like, hey, call it 6, and the next person's like, hey, call it 10. Like, I mean, how far do you go with this whole like let's round up thing?
okay.
And plus, do you really want to round up if it's your credit card charging you interest?
No.
If it's your credit card charging you interest, do you really want to round that up to 5.8? No. You were thinking this was money you were earning.
Yeah.
Yeah,
I thought I
no.
was scamming other people.
Yeah, you're scamming other people, but you don't know that that's money you're earning. That could be interest you're paying someone else. So in that case, let's round down. Call it 5.7,
That's true.
right?
Or
Okay.
let's just call it 4.
Yeah, ready? Yeah, call it 4. Call it free. All right, so there we go, folks. Do you want to do that process one more time, or shall we move on?
Move on.
Really? Now, folks, can I just show you something interesting? And I know. Anytime I use the word interesting, you're like, Mr. G, you're about to lie to us. But everybody try this out as an exercise, okay? Pick up your pencil. Everyone try this out as an exercise. A equals P 1 plus R over N to the NT. I'd like to solve for R right now. No numbers. So how do we do it? What do we do first?
Subtract P.
No, divide.
No,
Divide by P.
Divide.
So just like we were doing, so now we have A over P equals 1 plus R over N to the NT. Now what do I get rid of?
NT squared.
Yeah, we're going to root NT, the NTth root. But remember, we actually raised it to the power of 1 over NT. So we're going to raise both sides to the power of 1 over NT. So that's 1 over NT. And so that cancels out. What do we have now? We have A over P to the power of 1 over NT equals 1 plus R over N. Okay, and now what do we do? We're still solving for R.
Subtract 1.
Subtract the 1. So we have A over P to the 1 over NT minus 1 equals R over N. And now?
Divide or multiply by N.
And multiply it by N. So we multiply both sides by N. That cancels out, and we have this. Now, you folks, R equals N A over P to the 1 over NT minus 1. Is that a formula worth memorizing?
Yes.
No. Look how terrible that looks. It looks absolutely terrible. right? I mean, we already took the time to memorize this formula. That's all the formula we ever have to memorize for the rest of our life, right? Because you could, I just arbitrarily solve for r. Couldn't I now solve for n? Could I rearrange all this algebraically and solve for n? Could I solve it for t? Like, there's just something you do on the fly. The torture of memorizing every different arrangement of this formula, right? You just memorize the formula once, and then you do the algebra as you need to. Or, at dawn, you can memorize that formula. But, you know. Okay, so should we do one more, or are we done? What do you folks think? Because we would do the same process. Should everybody try once?
I think we should move on.
One person voted. Anyone else? What button? Should we do the next one? It's the same. Okay, we'll leave it. Let's keep going. So that was an example of solving for r. You might want to label that problem. Label that problem, solving for r. That way you can go back in your notes and remember that this is how you solve for interest rate. Okay. The next one says find the effective rate. This is really fun. Find the effective rate. Boy, I wish, well, I'll just move it over to here. 6% compounded quarterly. Now this is really interesting. What they're saying is, if you did 6% compounded quarterly, what is that the same as to someone who just got interest once at the end of the year? So let's do a simple example. Let's do a simple example and say, what if I just invested, so A equals P, 1 plus R over N to the NT. Let's do a simple example where I'm going to invest $1, and you get the quarterly interest divided by 4 for 1 year. Okay, so that's what we're going to do. We're going to invest $1 for 1 year and see how much we end up with. So is that fair? Did I plug all those numbers in right? We invest $1. It's quarterly, so that equals 4, and you do it for 1 year. So what do we end up with? That'd be 1 plus, well, hold on, 0.06 divided by 4, 0.06 divided by 4. That's 0.015, so 1.015 to the 4th. And so 1.015 is 14. That turns out to be 1.06136. So that's how much money I ended up with. Is that the same as getting 6% interest? What if I had only, really truly, what if I had only earned 6% simple interest on $1? How much money should I have? If you just did simple interest, I equals PRT on $1, so that's 1 times 6% for 1 year, how much interest would you end up with? Just 6 cents. I ended up with more than 6 cents. Yeah, kind of. So the effective interest rate here, I got more than just 6%. By the fact that I was compounding quarterly instead of once a year, I actually ended up with a little bit more money. And so the question is, how much more money? And so if you take away that $1 that you already put into the account, and you just look at how much interest you got, 0.06136, and you move the decimal twice, that's actually 6.13, actually rounding, 6.14 interest rate. So what we're saying here is that 6% compounded quarterly is the same as 6.14% compounded annually. So the fact that you got that interest 4 times a year instead of 1 times a year, effectively, you got more interest. And it's equivalent. 6% 4 times a year is equivalent to 6.14% annually. And I don't know if that seems like a huge gain. But I mean, if you're investing $1 million, that's a lot of money, a lot of extra money that you get. So now I'd like to give you the formula for it. The formula for the effective rate. So all the way up at the top there, you see where it says effective rate? The effective rate is 1 plus R over n to the n minus 1. The effective rate. Now you might say, well, why is that the formula? Essentially, you'll notice that what this formula is the compound interest formula without the p in front and without the t. Now what we're saying here is the t is actually there, but we're assuming t is 1 year. You're asking, what would the yearly interest be if t is just 1 year? And then we're really just saying p, let p be $1. So if you invested $1 for 1 year, how much would you end up with? And that's calculating into the effective rate. And you're subtracting 1 to get rid of the 1 point up front, so you can just focus on what the rate is. So what do we end up with? 1 plus 0.06 over 4 to the 4 minus 1. So I mean, we should get the same thing as what we just did. 0.06 divided by 4 plus 1. There's the power 4 minus 1. So yeah, did everyone get the 0.06? 136? Which is really, if you move the decimal twice, 6.136%. By the way, I just did number 14. That probably was not obvious. I skipped over number 13. I'm very sorry. I didn't come right out and say that. So we just did number 14. And so 6% compounded quarterly is the same as 6.136% computed annually. And that's what they mean by the word effective rate. So let's label both of those. This is the effective rate, because 6.13% has the same effect as this, which is the nominal rate. Nominal is a fancy word for name. Like, what is the name of that account? I'm putting my money into the 6% compounded quarterly account. And so that's what the bank claims to be giving you. That's the name on the account. We're claiming to give you 6% compounded quarterly. I mean, that's all a bunch of fancy smoke and mirrors. Like, break it down for me. How much am I actually getting by the end of the year? Right? So effective rate is like the bottom line truth. This is just something fancy to like get people's attention. So now everyone go back and do number 13. Yeah, because there were only 2 of those. So what would be the effective rate in number 13? Again, the effective rate is 1 plus r over n to the n minus 1. So it's darn near the exact same problem, 0.06 over 2 to the 2 minus 1. So 1.03 squared minus 1. What did you all get? You get 0.0609, which is really 6.09%. So you'll notice that no matter what, getting compounded interest is better than not getting compounded interest. And even going from just twice a year to 4 times a year, how much more interest did you get? It's not bad going from 6% to 6.09% to 6.14%. It begs the question, how high could that go? Like, what if I now compounded monthly? What would that be? And in fact, we can all do that on our calculators. What would it now be if you went monthly? So this was n equals 1. This was n equals 2. This was n equals 4. So what about monthly? How much higher do you think that 6% will go? So if you all do it, 1 plus 0.06 divided by 12, all raised to the power of 12 minus 1. It got all the way up to 6.17%. Is it increasing as rapidly as it started out increasing? How much did we increase by at first?
0.09.
And then?
0.05.
Yeah, 0.05, and then?
0.03.
0.03. So it's slowing down. What if I did 365 times a year? Right? Like, how much more interest could we get out of this? by compounding more times? I got 6.18%. So it's clearly not unlimited. Like as you compound more and more and more, the percent is going up, but it's not going to go up forever. Now what end value should we do just for funsies? Twice a day? Like if you got interest twice a day, then that would be 365 times 2, which is what? 730? So what if we did 730 times a year? That took us up to, it didn't even improve it. It's still 6.18%.
So 365 would be our cutoff.
Yeah, well, in this particular scenario. Okay, so now folks though, can I show you what's interesting here? The ultimate cap, what this formula of 1 plus r over n to the n minus 1 becomes as you let n become very, very big. So as n goes to infinity, you actually just get e to the r minus 1, where e is that number 2.718. And so now if I do e to the 0.06% and minus 1, it's 6.183.
What if it's leap year, so it's 366?
It'll barely make a difference. Yeah. Okay, so folks, circle that formula that you had. That was your effective rate. And make a little arrow. As n goes to infinity, the best effective rate, the best you can do in terms of compounding is just e to the r minus 1. And that's called not just compounded interest, that's compounded continuously. That's compounded continuously. So that is the end of the rainbow. The best you can do with compounding, like let's say you compounded your money 20 times a day or 100 times a day, you're still never going to do better than what is called compounded continuously, which maxes out at the effective rate of e to the r minus 1. And we are going to do some problems with e in the finance. Questions? Okay. All right. So we saw a problem where we wanted to solve for the interest rate. This problem, what are they wanting us to solve for? Find the amount that should be invested now to accumulate to this amount if the money is invested as it's said. So what are we trying to find? We're trying to find the principal. We're trying to find the principal. So writing down our formula first, A equals P, 1 plus R over N to the NT, where again we jot down all the things that we know, A, P, R, N, T. And the amount, find the amount that should be invested now to accumulate up to $2,000. So $2,000 is the amount of money we hope to have. The principal we don't know. The interest rate is 0.059. The number of times it's compounded is twice, semi-annually, and 2 years from now. So now again, this is an interesting goal-setting question. If I have a goal that 2 years from now I'd like to have $2,000, then how much money should I invest right now that it would grow into $2,000? So we plug in everything that we know, 2,000 equals P, which we don't know, 1 plus 0.059 over 2 to the 2 times 2. So we have 2,000. And again, this computation you're about to do, keep all the decimals in your calculator. So 0.059 divided by 2 plus 1, all raised to the power of 4. Did you all get the number 1.123324947? Super. Now again, do you have to write all of that down? Well, no, you don't have to write all of it down, but it better be on your calculator, all those decimals of accuracy. So now how do we solve for P?
And we just divide by all that. And so I'm just going to write down divide by 1.12. Obviously, I'm dividing by a lot more than 1.12. I'm going to type all those decimals of accuracy in so that I have this. But my calculator still has that number, so I hit 2,000, divide by that answer. Do you all know how to hit second answer? It's second negative sign. So do you all see on your calculator right above the negative symbol, it says ANS, that's answer. So if you hit second negative, it brings back up the answer you just had. So the principal came out to be 1780.428, so 0.43. Now, how could you solve for P now, algebraically? A equals P, 1 plus R over N to the NT. Remember how challenging it was to solve for R. How do we solve for P? P is being multiplied by all that. So you just divide by all that. And we have a formula for P. P equals A over 1 plus R over N to the NT. That's worth looking at because we're going to see some other formulas coming up here that look as bad as that. But that's a formula for present value. Present value. How much should you invest now to have a certain amount in the future? Now, again, is that a formula you need to memorize? No, because you can just manipulate the formula that you're given and get it. Okay, try the next one. Did anyone get 5,800? David, you did, or you just popping along?
Yeah.
Oh, okay, great. I wasn't sure if you were just dancing to the music. Now, folks, doing problems like these, you might say to yourself, surely now we have arrived at math that people use in their life. Like if you work at a bank or you're a financial advisor and you're actually trying to help people make financial goals. You're like, yeah, they're doing this. And yet, are they doing any of these calculations?
No.
They have an app or a website where you can just go and type in what you do know, and then it will just compute it for you, right? You all believe that, right? That no banker or financial analyst is actually sitting down with these formulas and crunching into this on a sheet of paper, because they just have an app or a website where you go, you type in what you do know, and it will calculate the rest. It's almost enough to make you sad, isn't it? Well, me anyway. All right, let's try some more. Now, this next one is going to be a little fun because you need to use logarithms and a graphing calculator. So let's look at some of these questions. These get really interesting. So let's look at the scenario. It's saying find the time required for the initial amount to be at least equal to the final amount. Now, this is interesting. This is like me saying, okay, I've got $1,000. I'm going to put it in the bank. How long do I have to wait until I have $1 million? Right? Like, that could be somebody's thought. Like, hey, if I just put some money in the bank and just wait long enough, eventually I'll have $1 million. Like if you're a vampire. If you're a vampire and you're immortal and you can live forever,
you'd have the time to wait. You can just put a little bit of money in the bank, wait a while, and then eventually you'll have all your money, right? So the big question is, how much time do you have to wait? How long would you have to wait? And then, of course, the sad thing is that with inflation in a given country, if you do wait that long, will inflation make that $1 million worth nothing anyway because of inflation? So let's try it out. We're going to deposit $8,000 now, and I want to know, how long do I have to wait to get $16,000? So that's the big question: is how long do I wait? How long do I have to wait? Anyone want to take a guess about how long you have to wait for 8,000 to become 16,000? How long?
A while.
30 years? Yeah, maybe 12 years? Now keep in mind, these numbers were not chosen at random. 8 to become 16, this is a classic example of double your money. Right? I mean, isn't that kind of what people are always trying to do when they gamble or hustle or commit a crime? We can double our money. Right? So that's what we're asking. How long do I wait to double my money?
14.
14 years?
Yeah.
Did you calculate it?
No.
Oh, okay.
I just looked at the back.
Oh, okay. All right. So it's 14 years. Now, again, here's the big question. Is it worth it? Is $8,000 worth waiting for 14 years for? I mean, how much money is that per year? If you take $8,000 and divide it by 14, how much are you really making?
570.
You're making $571 a year. And then if you divide that by 12, oops, 571 divided by 12.
47.
You're making $47 a month. And if you're doing that divided by 30 days in a month, I mean, you're talking about $1.50 a day. That's enough to make you depressed when you actually break it down to one day. I mean, $1.50, I can go outside and find $1.50 on the street right now, right? But that's what we're saying is, how long do I have to wait to get the same amount of money that every day I could just go out on the street and find $1.50? It's not worth it. So let's do it. A equals P. Well, it's a little worth it, because how long would it actually take me to go outside and find $1.50? At least 10 minutes of hustling, right? Yeah. Okay, so let's try it. 1 plus Rn VNT. We're always starting with the same formula, right? How long do I have to wait? So what are we solving for? What are we solving for? Time. So highlight your t variable. We're trying to solve for t. So how do we get t by itself? Well, first let's plug everything in. So I want to have 16,000. I'm investing 8,000. It's 5% interest, and it's compounded quarterly. So far we have that. So inside the parentheses, remember we just compute what's inside the parentheses and look at it. So that's 1.0125. So already I can just kind of look at that and say, hey, every time they compute me interest, I'm actually getting 1.25% interest. And so then, oh, by the way, well, okay, yeah, we'll leave it there for a second.
Can't you just divide the...
Well, yeah, I'm about to. So what do we do first?
Divide 8,000.
Divide by the 8,000, right? Because when we're trying to solve for t, this is slightly different because we're saying t is in the exponent. So eventually we're going to have to solve for an exponent, which means do a logarithm. But right now we'll divide up to 8,000. And the first thing I want you all to notice is this number 2 that's on the left-hand side. What does that number 2 right there represent? It represents the fact that you want to double your money. So had that been a 3, what would you be trying to do? Triple your money. And had that been a 4, quadruple your money. So that's interesting to note that this number right here represents your financial goal. You're dividing by the amount you want, by the amount you have. So that number is what you're trying to do to your money in a given time period. So now, how do we solve a logarithm? Should we do a simple example real quick? Let's say that we had 10 to the power of what equals 50. Do you all remember how to switch that into a logarithm? Remember that the first number stays first. This is log base 10. And then those two switch. Log base 10 of 50 equals x. That's how you just do a logarithm. So you take your exponential expression, and it's log base 10. Notice this is still the base. This is base to an exponent. So base to the exponent equals the answer. the base becomes the base of the log, but then you switch the exponent and the answer, so it's log base 10 of 50 equals x. Now all of you can do this log on your calculator right now. That's just the log button. So everybody hit log 50. Log 50, you'll get 1.69897. And that's what the exponent would be. So what did we just find out? We just found out that if you take 10 and raise it to the power of 1.69897, what will it equal? And I want you all to try it. Take 10 and raise it to the power of 1.69897, and what do you get?
49.99999.
Yeah. So 50, right? So everybody, go back in time to when you learned about logarithms, and just remember that a logarithm means, log means solve for an unknown exponent. So did everyone know that that's what logarithm means? Logarithm, the word logarithm means solve for an unknown exponent. So anytime there's a variable and an exponent, wow, you already know that you're going to have to use logarithms to do it. And where's our unknown? It's in the exponent. So you know you have to use a logarithm to do this. So how do we rewrite this thing? I'm going to write it backwards because I always find it easier. 1.0125 to the power of 4t is equal to 2. So remember, the base becomes the base, log 1.0125. And then you switch those two. So it's log base 1.0125 of 2 equals 4t. This is like a super fast review of logarithms. I assume that you've all studied logarithms at some point. Now, Don. Wait, did you say no?
Yeah.
I don't believe you. You did logs,
We
didn't
did
you?
logs together.
Yeah, exactly. Wait, you mean back in 150?
150 ended to.
Yeah, a long time ago. Okay. So now, how do we compute this? Remember, there's something else we need to remember, and that's the change of base rule. Does your calculator have a log base 1.0125 button?
Yes.
No. Your calculator only has log, which means log base 10, and ln, which means log base e. Wait, Luis, yours does, huh?
Yes, the fancy. Yes, the fancy.
Yeah, okay, Luis has a calculator that does it. For the rest of you, no, you do not. So, we cannot do log base 1.0125, so you have to do the change of base rule. And the change of base rule states, let me show it to everybody, that if you have log base 10 of b divided by log base 10 of a. And I just choose 10 because our calculator can do 10. So your calculator has a log button, that's log base 10. So now we can rewrite this as log 2, you don't even have to write log base 10 because log assumes log base 10, over log 1.0125 equals 4t.
But can we just hit math and then just plug it all in?
Not yet.
That's what I did.
What do you mean math?
Yeah, if you hit the math button and then scroll all the way down, and it says log base, and you hit that, and you just hit.
Oh, you have a fancy one too.
Oh,
So
yeah.
you and Luis both, you're in a special club.
Oh, cool.
Okay, but for the rest of us, now folks, one more thing before you do this computation. I don't want you to do the computation yet. Let's deal with the 4. We're going to get t by itself. That means divide off the 4, right? Another way of thinking about it, because I wouldn't want you all to write this. Right? That's visually displeasing. So what instead would we do? If you want to get rid of the 4, you could multiply by 1/4. Will that do it? If you multiply by 1/4, will that cancel the 4? So now over here, what happens if you multiply by 1/4? The 4 just goes into the denominator. So I want you all to see that when you have 4t, I'm going to do this in one step. If you have 4t equals all that, and you want to bring the 4 over, then you can, and the 4 goes into the denominator. So when we divide by 4, we really just end up saying log 2 over 4 log 1.0125. Okay? You are still dividing by 4, but you're doing it cleverly by multiplying by 1/4. And when you multiply by 1/4, the 4 simply goes into the denominator. Okay, so now you put parentheses on the denominator and divide the whole thing. You need a lot of parentheses, folks. You need parenthesis on the log 2, and then parenthesis around 4 log 1.0125. So everyone, let's see if you get the right answer. Parenthesis log 2 divided by 4 log 1.0125. Did anyone get t equals 13.949?
Yeah.
The back of the book, or the back of the paper said 14, so they rounded. But that's a fair thing to round because they're saying find the time required for it to be at least the final amount. And yeah, if you wait 14 years, it will be at least the final amount. Okay, now, anybody care to do the algebra with the letters instead? Yes, Mr. Chu, that sounds great. Okay, I thought so. A equals P. 1 plus R over N to the NT. And we want to solve for T. So we divide off the P. So A over P equals 1 plus R over N to the NT. And then we do a logarithm. So this would really be log of 1 plus R over N of A over P equals NT. But then we use the change of base rule to split that into a simple log. So then that would be log of A over P all over log of 1 plus R over N. And then the N gets divided into the denominator, and you get that. Okay, now folks, what do you think? Is that a formula worth memorizing? Anyone? Anyone? Not really. I mean, it's okay. But again, oftentimes it's easier just to derive a formula on the fly by just plugging in the numbers and then doing the simple work. That is a fairly nasty looking formula. I've been showing you these formulas all along because we're eventually going to get to a point where we have to use formulas like this because they've already done the derivation for us. Okay, everyone try one more. Try the next one. You're investing $7,900 at 5.2% compounded monthly, and you want to reach 25,200. Don't use that formula. Just use the original and do some algebra. And do your logarithm. Does it work?
I'll get back to you in like 3 minutes.
Okay. Yes, that was good. Yeah. Oh, I like the method. Good. Okay, great. Nice. Does it actually stop at that level, unfortunately? Oh, it's if you're repeating it. So maybe put the little line on top. That way you'll know later when you type it in your calculator and put more decimals.
Oh, it should be toward the back.
Nice.
Cool.
You're on that one, okay. Oh, that was the one. That was the one we did. Okay, okay, yeah. Good, good, good. Keep going. I'm going to start this one so you can all check your work when you get to it. So 25, 200. 7900. So first of all, that 25,200 divided by 7,900, that doesn't come out clean. So you'll need your calculator to keep all those decimals for you, or just write them all down. And then also the 0.0043333333, so I hope you all put a line on top of the 3. So then when we do our logarithm, it's log base 1.00433 repeating of 3.189873418 equals 12t, which you can then change that into log 3.1897418 all over 12 log 1.0043 repeating. So then to get this problem with as much accuracy as possible, you'd want to go back to get that 3.18 number by doing the 25,200 divided by 7,900. And once you have that number, then you could say parenthesis log of the answer. So by hitting second answer or second negative sign, you get that. And then divide by divide by 12 log 1.00433333333333333. And did anyone else get a t equals to 22.35?
No.
23.0638.
I got 24.20.
It's fascinating.
Oh, I see my problem. I did not have enough parentheses. Boy, those parentheses will get you. I got 59.88. Is that what you all got? Oh, no, that's still wrong because I had the wrong answer involved. All right, I'm going to stop and try that calculation again.
22.4.
This is log of 2520 divided by parenthesis 12 log 0.004.
That's 22 years and 4 months. So we're right.
Now I got it, 22.355. There. So is 22.35 or 22.36 anyway? Is that what everyone else got?
Yeah.
Okay. So you can see how you type it in your calculator really makes a big difference. I made a couple errors with my parentheses. All right. So we've reached. Okay. Okay. I'm moving along. The next few problems are word problems, but then again, they've been word problems all along. So how about we just set these up? We'll just set them up because these are just applications of what we've already seen. It's later. All right. So, oh, that's not a problem. There we go. If inflation is 4% per year compounded annually, what will it cost in 25 years to buy a house currently valued at $74,000? So this is a good, very practical question. What will inflation do to the value of different things in the future? So what would we write down? What do we write down? What formula will we write down?
Compound.
Yeah, compounded, right? I mean, that was the key word there, compounded annually. So long as we know that we're talking about compounded interest, we'd write down A equals P 1 plus R over N to the NT. And then we plug in everything we know. So they're saying inflation is 4% a year. So I know I can go ahead and plug in 0.04.
Are we skipping 21 and 22?
19 and 20.
And 19 and 20?
Oh my goodness. Oh yeah, boy, I skipped right on past that. Silly me. No wonder everyone was looking at me. No, I didn't want to skip those. Those are good problems. Oh yeah, we definitely want to do 21, 22. I'm sorry, folks. Let's go back to 19. Okay. We still get to use the same formula. So how long will it take for prices in the economy to double at a 5% annual inflation rate? So at no point in here do they say compounded. But the implication is still that we're using compounded interest. At least that's how I'm reading it. How long will it take for prices in the economy to double at a 5% annual inflation rate? Yeah, because whatever the value is, you're then tacking 5% on top of that. So whatever, let's say $1 is worth $1 this year, but by next year it's worth $1.20, then you're inflating that value. And therefore it's compounded interest because you're doing interest upon the final value that you got at the end of the last year. Okay, so how long will it take for prices to double? So what price should we talk about then? Like they don't tell us a given principal amount to write down. So could we just ask the general question, how long will it take $1 to become $2? Because they're saying how long will it take for prices to double? That's one way of doing it. You could just say, how long will it take $1 to be worth $2? Or if you wanted to be super specific, you could say, if your original principal is P, how long until it's 2P? Double. But even if I write down P and 2P, what could I do? If I go ahead and write down the rest of the formula, couldn't I just divide both sides by P? And then it would still just be the $1 becoming $2. So however you wanted to do it, whether you say how long until P becomes 2P or just how long for $1 to become $2, still the same formula. Okay, so how long will it take for prices to double at a 5% inflation rate? And it's annual, so it's 1 to the 1t. So what does that give us? That's 2 equals 1.05 to the t. Well, that really simplified tremendously.
What do we do with that one that you have in front? Yeah.
Well, if there's a 1 in front of anything, I mean, you could divide it off or you could just ignore it.
Oh,
yeah. So now, folks, I want you to see a fun activity.
I was like, why?
Yeah, because we're asking the question, how many times do I have to multiply 1.05 times itself to equal 2? So how many times do you have to multiply 1.05 times itself to equal 2? So everyone take your calculator, and in your normal calculator screen, type in 1.05, enter. So that's the original 1.05. Now hit times 1.05, enter. We've now multiplied 1.05 times itself twice, and now I'm at 1.1. So I am getting towards 2. So now what you can do is just start hitting the enter button. We've already done it twice, so now 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It took me 15 times to push the button for my 1.05 to be just over 2. Did anyone else get 15?
Yeah.
Was it 15 times you had to push the button? So in 15 times. So 1.05 to the 14th was only 1.97, and 1.05 to the 15th was that. So the actual answer is going to be between 14 and 15, probably 14.5 or something like that. So we can already kind of guess what the answer is going to be just by using our calculator a little bit. But now what we really want to do is do a logarithm. So this, again, is 1.05 to the t equals 2. So you do a log of 1.05 of 2 equals t. And so that's really change of base rule, log 2 divided by log of 1.5. And what will that give us? Log 2 divided by log 1.05. And the answer was 14.2. So I was a little off in my guess of 14.5, but it was indeed between 14 and 15. And by the way, provided that you're talking about annual inflation, provided n equals 1, the time to double your money is t equals log 2 over log of 1 plus r. Is that fair? That's what our formula ended up being. The 2 referred to doubling your money, and then the 0.05 was the interest rate. So is that a formula worth memorizing? Still probably not, because you can just memorize the original formula and then work backwards. Okay, looking at the next one though, you have money in an account at 2% interest compounded monthly to the next year. How long will it take? How long will it take for your money to double? So we'll just set this one up. We won't do the whole thing. Can I use that formula I just came up with? Log 2 divided by log of 1 plus r.
Yeah.
What was my assumption?
N equals 1.
Provided n equals 1, and here
12.
n is 12. So now I can't use it. So we just set the whole thing up and doubling our money. So again, how long for $1 to become $2? And that's at 2% interest for 12 compoundings, and we're solving for t. So now you would, have to solve 102 divided by 12. 1.0016 repeating all to the 12t. And so you'd have to solve that logarithm problem. And that's as far as I'll take it. But once you do the log and solve for t, I can't help it. Log 1.0016 repeating of 2 equals 12t. And then again, you use the change of base rule and then divide by the 12, which means you put the 12 in the denominator. So your final answer would be t equals log 2 over 12 log 1.0016 repeating. There. Does everyone agree with my final answer?
Yeah.
Once you do the change of base rule and then divide off the 12, so that would be it. And so we just calculated how long we have to wait for our money to double.
36 months.
Sorry, well, how long?
36 months, or is it years?
It's years,
So
but
36 years.
the answer is always years. Now, is that depressing? 36 years to
And
double
one
your money. What?
And 1 month.
Oh, yeah, I know that. Yeah.
So just a little over 36 years.
All right.
Just to double your money, how do you feel about that?
Where are we now? Number 21, right? Okay, we'll just do one of these. It's kind of nice. It's a 3-part problem. It's a 3-part problem. All right, so take a look at the instructions. It has part A, part B, and part C. And let's just look at all 3 of them at a glance real quick. So it says here, for the following amount at a given interest rate compounded continuously. So this is new, compounded continuously. This is now worth writing down over here on my formula board. Compounded continuously. I'll do it up here. So when you compound with n equal to infinity, and I know that sounds pretty weird. We were just talking about n equal to 1, 2, 4, 6, 12, 365. But if you let n equal infinity, then the formula becomes a equals p times e to the rt, where e is Euler's number, so named after him, 2.718281, etc. So it's very similar to the first formula. You have a p, you have a base, product of t. I oftentimes just think of this formula as PERT. Did any of you ever use PERT plus shampoo in the 90s?
I was
Pert.
born at the end of
Okay, maybe not then. But anyway, PERT plus shampoo was green. It was green shampoo. Oh, I can smell it now. All right, so we're using compounded continuously. Now it says find the future value after 9 years, find the effective rate, and find the time to reach $10,000. So let's try this out. We have here $4,400 we're going to invest at 4.6% interest. And we could go ahead and just do this one. So how much money will we have at the end of 9 years? So A equals the amount, P, so the principal, 4,400, e to the 0.046 interest rate, and how many years?
9.
So a very, very easy problem. You just type it in your calculator. Be very careful with your calculator. Put parentheses on the whole exponent. Be 4,400 times e to the, and then within that 0.046 times 9. Make sure that the entire exponent on e is in parentheses, so that the 0.046 times 9 is what is being raised to e as an exponent. If you do it correctly, it should turn out to be 6,656.57. All right, now how about part B? Here they're asking for the effective rate. So remember, moments ago we said the effective rate was 1 plus r over n to the n minus 1. And that was the chunk inside the formula, a equals p 1 plus r over n to the nt. So now we're looking at the formula p e to the rt. And remember, we let t equal 1, we let p equal 1. And whatever you have left, you subtract 1 from it. So if you let p equal 1 and t equal 1, all you have is e to the r, and you subtract 1 from it. So that's your effective rate, e to the r minus 1. And so we do e to the 0.046, subtract 1. And this is going to tell us effectively what interest rate we just got, which was 0.047074. Move the decimal twice, and it's really 4.7%. What were they advertising the account as? 4.6%. But yeah, bucko, because I got compounded continuous interest rate, I was actually earning 4.7%. And then finally, they're asking how long until the amount reaches 10,000. So it took 9 years to reach 6,000. How long do you think it'll take to reach 10,000? It took 9 years to only increase by 2,200. And we want to increase it all the way up to 10,000. So maybe 18 years, maybe 20 years, maybe 30 years. So we would set A equal PERT. And you'd say, when is it going to grow to 10,000 from 4,400? So that's e to 0.046. And t. Hey, since we want to solve for time, what are we going to have to solve for? Or how are we going to have to solve for t? Since t is an exponent, we'll have to use a logarithm. So this will be our last problem. We do 10,000, divide off the 4,400. So that gives us 2.27 repeating equals e to the 0.046 t. And now our calculator does actually have a logarithm for this. This is, if you want to write it backwards, e to the 0.046 t equals 2.27. When you do log now, you say log base e of 2.27 equals 0.046 t. Well, what is log base e? On your calculator, what is log base e? It's your other button, ln. ln is simply the button for log base e. So this is really ln 2.27 repeating equals 0.046 t. So dividing off the 0.046 t, we have that t is equal to natural log of 2.27 all divided by 0.046. So natural log of 2.272727272727 divided by 0.046, and the time is 17.8 years. How do you all feel about these finance problems that we did today?
Easier.
Easier than the matrix? Shorter? Well, that's true. I mean, matrix problems are very long. The good news is that today we finished just kind of the core computational ability of the finance chapter. When we come back on Thursday, we're going to get to some finance questions, which are weird, like crazy, like a lot more sophisticated in terms of the question that you're asking, and a lot more sophisticated in terms of the formulas. Like all day now, we've just been rehashing the same formula, 1 plus r over n to the nt. But next time, we'll get to problems that use wildly different formulas and solve for wildly different results. Sorry about that.